Hello, this is Mr. Field, and this is my video on kinetic energy and gravitational potential energy. Now, before you watch this video, make sure you've watched the previous ones on scalar and vector quantities and conservation of energy, as both of those contain concepts that this video relies on. So check out earlier in the playlist if you need. Now, in this video, we'll be looking at kinetic energy and the calculations for it, gravitational potential energy and the calculations, how we convert between GPE and KPE, and then finally advanced calculations that combine the two different ideas. Okay, so let's look first of all at kinetic energy. Now, kinetic energy is the energy stored in moving objects, and because it's a store of energy, it has the units of joules like that, and sometimes obviously kilojoules as well, depending on exactly how the units are presented. Now, the kinetic energy of an object is determined by two things. Thing number one is its mass, and thing number two is its speed. So increasing both the mass and the speed affect the kinetic energy, but not in the same way. So if we look at the equation for kinetic energy, we can see that kinetic energy is half multiplied by the mass multiplied by the velocity squared. That means the velocity has a bigger effect on the kinetic energy than the mass does. We can look at that in symbol form as well. So we say KE for kinetic energy equals half times m times v squared. And here is the equation triangle for that as well. KE at the top and then half times m times v squared on the bottom. So let's look at our first example. Example number one. Calculate the kinetic energy of a 420 kilogram horse galloping at 11 meters per second. Now let's work through Vesrau. So we're going to star our target. The target is the kinetic energy. Underline the values. So 420 kilos and 11 meters per second. Let's copy out the values. So we're going to say KE equals, I'll put a star there because that's what we're trying to find out. M, the mass, is 420 kilograms, and v, the velocity, is 11 meters per second. Now, we don't need to convert any units because we've got kilograms and meters per second, which is the appropriate units already. So next, we go for our equation. We say KE equals half multiplied by m multiplied by v squared. I strongly recommend you always write out the equation you're going to use because it just makes it so much easier to put the numbers in the right place. Now, we're going to leave KE as KE because we don't know what it is, but the rest of it we can substitute. So we're going to say half multiplied by m, which is 420, multiplied by v, which is 11, and square it. Now, let's just do this step by step to avoid making mistakes. So we're going to say KE equals half times 420. Now 11 squared is 121, so we're multiplying this by 121. And if we stick all this into the calculator, we get a kinetic energy answer of 25,410, and the units is joules as our final answer. So 25,410 joules. Example number two. Calculate the kinetic energy of a 6,800 gram bowling ball bowled down its lane at 8 meters per second, giving the answer in kilojoules to three significant figures. Okay, let's work through Vesrau again. So we're going to start with starring our target, which is the kinetic energy. Underline the values. I've done that already. Now we're going to copy out the values. So we'll just put KE equals star because that's what we're finding out. M, our mass, is 6,800 grams. Make sure we put those units in. And V, our velocity, is 8 meters per second. Now, this time we do need to convert some units because the mass has been given in grams and we need it in kilograms. So there are 1,000 grams in each kilogram. So to do that conversion, we're going to divide by 1,000, and that is going to give us 6.8 kg. So now let's put our equation. KE equals half multiplied by m multiplied by v squared, which is half multiplied by 6.8 for our mass, not 6,800, multiplied by v squared, so v is 8, and don't forget the square. Let's do this really slow, so half times 6.8, and that 8 squared becomes 64, put that all into the calculator and we get a final answer of 217.6 joules. But remember, it asks for it in 3 significant figures. So we need to look at our 4th significant figure here. And because that is greater than 5, or 5 or more, we're going to round it up. So to 3 significant figures, this will be 218 joules. Bish bash bosh. Okay, example number 3. Bit of a harder one this time, so more of a higher tier because it's going to involve some rearrangement. So a lorry driving at 25 meters per second on the motorway has 9,375 kilojoules of kinetic energy. Calculate its mass. So let's work through Vesrel. So star the target is the mass. Put a little star there to remind us that's what we're finding out. Underline the values, I've done that already. Copy those values out. So we're going to say KE equals 9,375 kilojoules. Don't forget the units. M equals star because we don't know that, and the V, the velocity, is 25 meters per second. Next, make sure we convert any units. Now we are going to need to convert units because we've got kilojoules here. And we want it in joules. So remember, kilo means 1,000. So to convert that into joules, we're going to multiply by 1,000, and we'll get 9,375,000 as our answer in joules. Now, once we've got all the values sorted, we can get on with our equation. So the equation is KE equals half multiplied by m multiplied by v squared. So we can say the KE was 9,375,000 equals half multiplied by m, our unknown, multiplied by 25, that's our velocity, squared. Now, we need to rearrange this to make m the subject, but before we do that, let's simplify as much as we can. Now, we've got the half here, and we've got the 25 squared there. So 25 squared is actually 625, and half of that will be 312.5. So we can simplify this like this. We can say 9,375,000 joules equals 312.5 multiplied by m. So therefore, to make m the subject, we're going to need to do the inverse operation. So it's being multiplied by 312.5, so we're going to divide both sides by 312.5. Do that on each side to keep the equation equal. And we get m equals 9,375,000 divided by 312.5. And that gives us a final answer of 30,000 kilograms as the mass of our truck. Okay, so let's look at our final example then. Again, another higher tier example. It's going to have a harder rearrangement this time because we're going to be trying to find V, and remember V squared appears in the equation rather than V, so that's going to complicate things slightly. So let's see how this pans out. So we have a cyclist and their bike with a combined mass of 85 kilograms, has a total of 9.5 kilojoules of kinetic energy. Calculate its speed to 1 decimal place. So let's star our target. The target is the speed. Let's put a little star there to remind us that's what we're finding. We've already underlined the values, so let's copy those out. We have KE, kinetic energy, equals 9.5 kilojoules. The mass is 85 kilograms. And finally, the velocity or speed is a star, is unknown, so we'll just leave that as a star. Now, we do need to convert some units again because we've got kilojoules. We need to multiply that by 1,000. Because remember, kilo means 1,000. So that will give us 9,500 joules as our kinetic energy. Okay, now we're good for the equation. So let's write it out. Same as always. KE equals half multiplied by m multiplied by v squared. So now we can substitute in. So our kinetic energy is that 9,500. So we can say 9,500 equals half multiplied by our mass, 85, multiplied by v squared. Now, we're going to need to start doing a whole load of rearranging, first to make v squared the subject, and then to find v itself. So before we do that, let's just simplify what we can. Now, we've got half multiplied by 85, so we can simplify that to this, we can say 9,500 equals half times 85 is 42.5 times v squared. Now, to make v squared the subject, we've got to do the inverse operation of whatever's happening to it. So it is being multiplied by 42.5. So we divide by 42.5 because that is the inverse. And we have to do that to both sides to keep the equation equal. So this gives us v squared ends up equaling 9,500 divided by 42.5, which equals 223.529, blah, 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 blah. I would tend to just keep that value in my calculator rather than writing out the whole thing, because then you just risk a copying error and ruining your calculation. Now, so if v squared equals 223.529, the inverse of squaring is the square root. So if we square root both sides, we get v equals the square root of 223.529, which equals 14.951, blah, 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 blah. Now, if you note in the question, it asked for the answer to 1 decimal place. So we need to round this appropriately. So if that is our first decimal place, we've got to look at that 5 there. Now that 5 is high enough to round upwards. So the 9 rounds up kind of to 10. So we turn the 9 into a 0 and turn the 4 into a 5. So to 1 decimal place, the answer here would be the velocity equals 15.0. And don't forget the units. This is velocity, which is meters per second. And that's our final answer. The next calculation for us to do is to look at gravitational potential energy. Now, gravitational potential energy, often abbreviated to GPE, is the energy stored in an object based on its position in a gravitational field. And it's affected by 3 things. So objects have more GPE when they are higher up, when they've got more mass, and when gravity itself is stronger. So we can calculate it this way. So rather than calculating the gravitational potential energy, we tend to calculate the change in gravitational potential energy. So the change in gravitational potential energy equals the mass in kilograms multiplied by the gravitational field strength, that's the strength of gravity, multiplied by the change in height. Or in symbol form, we say delta GPE equals m times g times delta h. Now, I'm saying delta, but you might not be seeing it. That triangle symbol, that is the Greek letter delta, which is their version of the letter D. That's specifically a capital delta there. And this is always used in physics to represent change. So when we say delta GPE, we mean change in GPE. When we say delta H, we mean change in H. Now, it's just worth talking a little bit about this value here, G, the gravitational field strength. Now, on Earth, the gravitational field strength is 10 newtons per kilogram. That means that 1 kilogram weighs 10 newtons, 2 kilograms weighs 20 newtons, 3 kilograms weighs 30 newtons, and so on. Now, that is the only value that you're expected to remember. You might sometimes be given questions that deal with different places like the moon or Jupiter or Mars or something. In those cases, you'll be given the gravitational field strength. But in these ones, in any question based on Earth, you are expected to remember that it's 10. It's also worth bearing in mind that the real value is actually something closer to 9.8. And if you use that value in the exams, you will still get the marks. But honestly, keep it simple. Go with 10, because although it's not quite right, it is what the examiners are expecting to see, at least on the Edexcel syllabus. Now, the equation triangle for this looks like this. So we've got delta GPE at the top, and then m, g, and delta h on the bottom. So let's look at example calculation number 1, very much a foundation tier question. An astronaut with a mass of 120 kilograms falls 20 meters into a crater whilst exploring the moon. Calculate the change in GPE if the gravitational field strength is 1.6 newtons per kilogram. Give your answer in kilojoules. So let's star our target. We're trying to find the change in GPE. Underline the values, done that already. Copy out those values. So we're going to say delta GPE. Well, we don't know that, so we're going to leave that as a star. M, the mass, was 120 kilograms. G, the gravitational field strength, is 1.6 newtons per kilogram. And finally, delta H, the change in height, well, the person falls 20 meters, so 20 meters is our change in height. Let's convert any units we need. Now, they're all in the right units, so that is all done. So now we can move straight on to the equation. So we can say delta GPE equals M multiplied by G multiplied by delta H. So now we can just substitute in. So we can say M was 120 kilograms. That was that value there. Multiplied by G, which was 1.6 newtons per kilogram. Multiplied by the height change, which is 20 meters. And if we stick that all into the calculator, we're going to get an answer of 3,840 joules. But we're not quite finished because it wants the answer given in kilojoules. That's stated in the question. Remember, there's 1,000 kilojoules, so 1,000 joules in each kilojoule. So to convert joules into kilojoules, we're going to divide by 1,000, and that will give us a value of 3.84 kilojoules, and that's our final answer. Example number 2. A forklift truck transfers 56,000 joules of GPE when it lifts a 1,400 kilogram pallet of bricks. How high does it lift it? Now, this is more of a higher tier question because we're going to have to do a rearrangement. So let's see how this works out. Star our target, first of all. So how high does it lift it? That is our target. Now, how high, really what we're talking there, we're being asked to find delta H. Underline the values. We've got 56,000 joules and a 1,400 kilogram pallet of bricks. Copy those values out. So delta GPE equals 56,000 joules. M, the mass was 1,400 kilograms. G, now it doesn't mention or specify where we are, so it can be assumed that this is on Earth. I don't believe we've ever taken a pallet of bricks in a forklift truck to any other places other than Earth. So given that it's Earth, we can say that G is 10 newtons per kilogram. So unless it specifies another place, always go with 10 as your value. And we're being asked to find delta H, so we'll leave that as a star. So now we can write out the equation. Delta G PE equals M times G times delta H. Let's substitute in. So we've got 56,000 equals our mass was 1,400 multiplied by our value for G, which is 10, multiplied by delta H, which we don't know. So we're going to have to rearrange this to make delta H the subject, but let's simplify what we can first. We've got 1,400 multiplied by 10, so we can make this into 56,000 equals 14,000 multiplied by delta H, because 14,000 is 1,400 times 10. Now we can rearrange. So to make delta H the subject, we do the inverse operation. So rather than multiplying by 14,000, we divide by 14,000. But we've got to do that to both sides. So we end up with delta H equals 56,000 divided by 14,000. And if we put that into the calculator, and some of you will be able to do it in your heads as well, we end up with an answer of 4. And don't forget our units of meters. And there we go. That's our final answer. Example number 3, another higher tier one. It says a space probe loses 46.25 mJ of GPE. Now, M means mega. So this is 46.25 megajoules of GPE. So it loses 46.25 megajoules of GPE when it descends 10 kilometers to land on the surface of Mars. Calculate the probe's mass if the gravitational field strength is 3.7 newtons per kilogram. So let's, as always, work through Vesrel. So we're going to star our target, which is to find the mass. Underline the values, already done. Let's copy those values out. So we've got the delta GPE is that 46.25 mJ. Make sure we copy the units out. Then we have the mass, which equals a star, we don't know it. We've got G, which equals 3.7 newtons per kilogram. And finally, we've got the delta H. It's descending by 10 kilometers. Let's move on to the unit converting step. Now, there are actually 2 units to convert here. Now, I've given you these funny units, megajoules for GPE, because although it doesn't come up very often in the exams, you are expected actually to know what megajoules means. Now, mega refers to a million of something. So kilo means 1,000 of something, mega means a million. So this is 46.25 million joules. So to do the conversion, we're going to multiply by a million. 1 times 10 to the 6. And that's going to give us 46,250,000 joules for our delta GPE. And then for the kilometers, now kilos easier. We know kilos are 1,000, so we're just going to multiply that by 1,000 to give us a delta H of 10,000 meters. So now we've got all our numbers in line. Let's write out our equation. So the equation is, as always, delta GPE equals m multiplied by g multiplied by delta H. Do not be tempted to skip this step. It really makes a big difference. Makes it much easier to pick out the right numbers. So our delta GPE we just saw was 46,250,000 equals m times g times delta H. So m is the star. We don't know that. We'll just leave it as m. G was 3.7. And our delta H was 10,000 meters. Now, we are going to need to rearrange to make m the subject, but let's simplify what we can first. So we'll leave the 46,250,000 untouched for now. That equals m multiplied by 3.7 times 10,000 is 37,000. So 46,250,000 equals m multiplied by 37,000. So to make m the subject, we do the inverse operation of multiplying by that. So we divide both sides by 37,000, like this, which leaves us with m equals 46,250,000 divided by 37,000, and that comes to 1,250 kilograms as the mass of our space probe. Now, a common kind of question is in exams is to explore the relationship, the kind of interplay and interchange between kinetic energy and gravitational potential energy. So, example, imagine a ball rolling down a hill. At the top of the hill, we can think about the ball only in terms of its GPE. It's got lots of energy in its GPE store, and because it's not moving yet, no energy in the kinetic energy store. Now, as it rolls down the hill, the energy is converted from gravitational potential energy to kinetic energy. So halfway down the hill, the ball will have roughly half the amount of GPE and a similar amount of KE. And then by the time it's got to the bottom of the hill, it's got no energy left in that GPE store, and all of it is being converted to the kinetic energy store. So really importantly, the amount of kinetic energy it's got at the bottom of the hill is equal to the amount of gravitational potential energy it had at the top of the hill, or more specifically, the amount of gravitational potential energy it's lost between the top and the bottom of the hill. Now, in reality, this isn't quite true, because we know, because of the effects of dissipation, that as it's moving through the air and rolling along the ground, there will be friction and air resistance, causing some energy to be transferred to the thermal energy stores of both the ball and the air. So actually, there'll be a little bit of energy loss as well, which is shown as that red bar for thermal energy just there. Now, another example might be, throwing a ball up in the air. You all had this experience, with bouncy balls and things like that. You drop a bouncy ball on the ground, and it doesn't bounce back quite as high as you dropped it from. And the reason why is that as the ball moves up through the air, kinetic energy is converted to gravitational potential energy. And then as it falls down, the GPE, gravitational potential, is converted back to kinetic energy. But when it bounces, it cannot bounce back as high as it fell from, again because of dissipation. While that ball's moving through the air, air resistance transfers some of its energy to thermal energy rather than GPE or KE. And equally, when it bounces, the friction of the particles moving against each other inside the ball transfers energy to thermal energy as well. And so that means that our energy gets dissipated, so it can't bounce back as high each time. Now, we might also be asked to do some calculations based on this principle. Now, fortunately, when you do these kind of calculations, we're only going to be looking at GPE and KE, and we will ignore any energy loss by dissipation, because that will make things too complex at this level. So let's look at this then. Advanced calculation number 1. Imagine a 5 kilogram mass is dropped 40 meters. How fast will it be traveling just before it hits the ground? And it says assume no dissipation of energy. So the key to this question is to recognize that the GPE that the mass has at the top before it's dropped will exactly equal the KE, the kinetic energy, just before it hits the ground. So if we can calculate the GPE, that will allow us to solve the velocity using the KE equation. So let's find the GPE first. So we can say delta GPE equals m times g times delta h. Now, the mass is 5 kilos. That was given there. It doesn't state the value of g, but I've said before you can assume it's 10 unless otherwise stated, because we can assume it on Earth. So 5 times 10, and our delta h, the mass is 40 meters up in the air, so delta h will be 40. So we've got 5 multiplied by 10 multiplied by 40, which gives us a delta GPE of 2000 joules. So because of this equivalence up here, that 2000 joules, as well as being the delta GPE, that is also our KE. So now we can find the velocity. So if we write out our kinetic energy equation, we can say KE equals half multiplied by m multiplied by v squared. Now, because of this equivalence, that 2000 we just found is our KE as well. So we can say 2000 equals half multiplied by the mass, which is 5 kilograms, multiplied by v squared. Let's simplify before we rearrange. So we can say 2000, half times 5 is 2.5, so we can just say is 2.5 times v squared. We're going to need to rearrange now to make v squared the subject, so it's being multiplied by 2.5, so the inverse is dividing by 2.5. Divide 2.5 on both sides. So we end up with v squared equals 2000 divided by 2.5, so v squared equals 800. And then finally, we need to get v on its own, so v is being squared. The opposite of that is to square root it, but we've got to square root both sides to keep everything equal. So we end up with v equals the square root of 800, which comes out to 28.284 blah 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 blah. Now, if the question doesn't specify, your best kind of default assumption is to round things to 3 significant figures. So that's our third significant figure. The 8 there is enough to is enough to round up. So we're going to say v equals 28.3 meters per second as our final answer. Let's look at example number 2. We're going to use the same kind of idea, but we're going to work in the opposite direction this time. So it says a 5.4 kilogram ball is fired directly upwards. When it leaves the cannon, it is moving at 110 meters per second. Calculate the maximum height it reaches. Assume no energy dissipation. So again, we're going to use this idea that the KE, when the ball has just left the cannon, is going to be equal to the GPE, or the delta GPE really, at the cannonball's highest point. So we've got all the information we need to find the KE. So let's do that first. So we can say KE equals half multiplied by m multiplied by v squared. So that is half multiplied by the cannonball's mass, which is 5.4, multiplied by v squared, so that is 110 squared. And if we put that all into the calculator, that gives us a value for KE of 32,670 joules. Now, importantly, because of this relationship, that value is also our delta GPE. So we can use that in the delta GPE equation to then find our height change. So let's write out the delta GPE equation. So we can say delta GPE equals m multiplied by g multiplied by delta h. Delta GPE was 32,670. That's the value we just calculated. Equals the mass, 5.4 kilograms, multiplied by g. Again, it doesn't say g, but because we're on Earth, unless it specifies otherwise, we can assume we're on Earth. So we're going to call that 10 multiplied by delta h, which we don't know. So let's simplify before we rearrange. So we're going to say 32,670 equals 5.4 times 10, that is 54 times delta h. Divide both sides by delta h, doing that inverse operation. We get delta h equals 32,670 divided by 54. And that will come to a final answer of 605 meters. Bish bash bosh. Okay, there we go. That's it. The end. As always, thank you for listening and well done if you got this far.